Hello, everybody. My name is Simon Doclo. I would like to thank the conference organizers for inviting me to present our work on cognitive-driven binaural beamforming for hearing devices using EEG-based auditory attention decoding. This is mainly work from my PhD student Ali Arudi while he was working in the University of Oldenburg in Germany. During the last decades, significant advances have been made in single and multi-microphone speech enhancement algorithms for hearing aids and cochlear implants. Although several algorithms are available to reduce background noise or to perform source separation in multi-talker scenarios, their performance crucially depends on correctly identifying the target speaker to be enhanced. Often the target speaker is assumed to be either located in front of the hearing device user or to be the loudest speaker. However, in real-world conditions, these assumptions are often violated. Recent advances have shown that it is possible to infer the auditory attention of a listener from single trial EEG recordings. Several auditory attention decoding methods have been proposed to identify the attended speaker based on, for example, least squares cost function, neural networks, or Bayesian filtering. Aiming at incorporating auditory attention decoding into speech enhancement algorithms, several cognitive-driven algorithms have been proposed in the last couple of years. These, for example, first try to separate all speakers from the mixture and then select the attended speaker based on the EEG recordings or are based on multi-channel Wiener filters. In this presentation, I will discuss a recently proposed and published cognitive-driven binaural beamformer, which enhances the attended speaker and controls the suppression of the unattended speaker, while preserving the spatial impression of the acoustic scene. It is a relatively simple system, which is designed to work in realistic, noisy, and reverberant acoustic environments. The outline of the presentation is as follows. First, I will review the considered least squares-based methods for auditory attention decoding and discuss its performance in the noisy and reverberant acoustic scenario with two competing speakers. I will then present the proposed cognitive-driven binaural beamforming system, where beamformers are both used to generate reference signals for decoding, as well as to generate binaural output signals. For the beamformers, we will consider either minimum variance distortionless response or linearly constrained minimum variance beamformers. In the last part of the presentation, I will then present the evaluation results of the proposed system for a noisy and reverberant scenario with two competing speakers, both in terms of decoding performance as well as in terms of speech enhancement performance. In the first part, I will briefly review the used least squares-based auditory attention decoding methods. It should be noted that nowadays faster and more robust decoding methods are available, but this is the method we used for our experiments. The used AAD method aims at reconstructing the attended speech envelope from the EEG recordings using a trained spatial-temporal filter and consists of two steps, a training step and a decoding step. In the training step, the attended speech signal is assumed to be known. From this signal, the attended speech envelope EA is computed. A spatial-temporal filter G is then computed by minimizing the least squares error between the attended speech envelope and the envelope reconstructed from the EEG recordings R, regularized with the squared L2 norm of the derivatives of the filter coefficients to avoid overfitting. In the decoding step, the envelopes of two reference signals, for example, the clean signals of the speakers, are compared with an estimate of the attended speech envelope, which is computed using the trained spatial-temporal filter. If the correlation coefficient between envelope 1 and the estimated speech envelope is larger than the correlation coefficient between envelope 2 and the estimated speech envelope, then speaker 1 is identified as the attended speaker and speaker 2 as the unattended speaker. Let's now have a look at the decoding performance of this method, and more in particular, investigate the influence of noise, reverberation, and an interfering speaker in the reference signals used for decoding. For the experiments, we considered an acoustic scenario with two competing speakers, one at the left side of the listener at -45 degrees and one at the right side at +45 degrees. As clean speech signals, we used two German audio stories uttered by two different male speakers. The acoustic stimuli were generated by convolving the clean speech signals with non-individualized binaural impulse responses, either measured in an anechoic or reverberant environment and by adding diffuse babble noise. The acoustic stimuli were presented to the participants using insert headphones. We considered four experimental analysis conditions: noiseless, that is without noise and reverberation; reverberant, that is with two different reverberation times but no noise; noisy, that is with diffuse babble noise at two different SNRs but without reverberation; and then the most realistic condition, including noise and reverberation. 18 native German-speaking participants took part in the study. Among all participants, 8 participants were instructed to attend to the left speaker, while 10 participants were instructed to attend to the right speaker. The EEG responses were recorded using an EEG cap with 64 electrodes at a sampling frequency of 500 Hz. The EEG responses were bandpass filtered between 2 and 8 Hz and subsequently downsampled to 64 Hz. The envelopes of all considered speech signals were obtained using a Hilbert transform, followed by low-pass filtering at 8 Hz and also downsampling to 64 Hz. For the training and decoding steps, the EEG recordings were split into trials, each of length 60 seconds. For filtered training and evaluation, each participant's own data were used. The decoding performance was then computed by averaging the percentage of correctly decoded trials over all considered trials and all participants, where we used a leave-one-out cross-validation approach. Let's now have a look at the average decoding performance, and more in particular, the influence of noise, reverberation, and an interfering speaker in the reference signals used for decoding. To investigate the influence of noise, we compare the decoding performance in the noisy condition without reverberation between using the clean signals and the noisy signals as reference signals, that is the blue and yellow bars. It can be observed that for the considered SNRs, a comparable decoding performance is obtained. Similarly, to investigate the influence of reverberation, we compare the decoding performance in the reverberant condition without noise between using the clean signals and the reverberant signals as reference signals. Again, the blue and yellow bars. It can be observed that for the considered reverberation times, also a comparable decoding performance is obtained. Lastly, to investigate the influence of an interfering speaker, we compare the decoding performance in the reverberant noisy condition between using the clean signals and the binaural microphone signals, which contain noise, reverberation, and an interfering speaker. As expected, the decoding performance now significantly decreases when using the microphone signals as reference signals for decoding. Hence, these results show that using the least squares-based method, it is feasible to decode auditory attention in realistic acoustic environments with noise and reverberation. Not unexpectedly, the best decoding performance is obtained when using the clean speech signals as reference signals for decoding. However, since in practice the clean speech signals are obviously not available, the reference signals need to be generated from the binaural microphone signals. Several methods have been proposed to generate reference signals, for example, using speaker separation algorithms based on deep neural networks or using beamforming algorithms. Since the interfering speaker has the largest influence on the decoding performance, the main objective of these algorithms should be to suppress the interfering speaker. In this work, we will mainly focus on investigating several well-known beamformers to generate reference signals for decoding. Aiming at integrating auditory attention decoding into speech enhancement algorithms, in the second part of the presentation, I will present our cognitive-driven binaural beamformer. The proposed binaural beamformer is steered based on auditory attention decoding and the estimated direction of arrivals of the attended and the unattended speaker. The system consists of 3 stages. The first stage is acoustic scene analysis, where the DOAs of both speakers are estimated from the binaural microphone signals. Based on the estimated DOAs, in the second stage, 2 beamformers then generate appropriate reference signals for auditory attention decoding. One beamformer aims at enhancing speaker 1 and suppressing speaker 2 and background noise, whereas the other beamformer aims at enhancing speaker 2 and suppressing speaker 1 and the background noise. Using the beamformer output signals as reference signals, the least squares-based AED method then identifies which DOA corresponds to the attended speaker and which DOA corresponds to the unattended speaker. In the third stage, a binaural beamformer generates binaural output signals passing through the attended direction without distortion and suppressing the unattended direction while preserving the spatial impression of the acoustic scene. We consider 2 types of beamformers. On the one hand, the minimum variance distortionless response, or MVDR beamformer, minimizes the noise PSD and passes the estimated target direction without distortion, while the linearly constrained minimum variance, or LCMV beamformer, additionally suppresses the interference direction with a factor delta smaller than 1. First, we expect LCMV beamformers to generate better reference signals for decoding than MVDR beamformers, since they allow to suppress the interfering speaker more than MVDR beamformers. An additional advantage of using an LCMV beamformer to generate binaural output signals is that it allows to control the suppression of the interfering speaker, which may be important when intending to switch attention between speakers. To implement these beamformers, a number of quantities are required. First, the noise covariance matrix 5e, for which often a diffuse noise field is assumed. Second, the so-called relative transfer function, or RTF vectors A of the speakers, for which we will either consider anechoic or reverberant RTFs. Anechoic RTFs simply correspond to head-related transfer functions for a certain direction. They are also sometimes referred to as steering vectors in beamforming literature. Reverberant RTFs can be considered as an extension of anechoic RTFs, which also take into account reverberation effects. In the last part of the presentation, I will present the evaluation results of the proposed system for a noisy and reverberant scenario with 2 competing speakers, both in terms of decoding performance as well as in terms of speech enhancement performance. For the experiments, we considered the same acoustic setup as discussed before, with 1 speaker at -45 degrees and 1 speaker at +45 degrees. As input signals for the beamformers, we used all available binaural microphone signals, that is 3 microphone signals on each hearing device. We also only consider the most interesting acoustic scenario, which includes reverberation and diffuse babble noise. I will briefly discuss the implementation details of the different stages of the beamforming system, where for each stage, we either assume that oracle information is available or the required parameters are estimated from the binaural microphone signals. For the first stage, acoustic scene analysis, we either assume that the DOAs of both speakers are perfectly known or are estimated from the microphone signals. Of the many available binaural source localization algorithms, we used an algorithm that estimates the source presence probability for each DOA by means of support vector machine classifiers using generalized cross-correlation features. As already mentioned before, For the NVDR and LCMV beamformers, several quantities are required. For the noise covariance matrix, we used a diffuse noise field. For the RTF vectors, we considered both reverberant as well as anechoic RTFs, where anechoic RTFs basically only depend on the DOA. It should be realized that jointly estimating the reverberant RTF vectors of two simultaneously active speakers is not at all straightforward, whereas estimating the DOAs of two simultaneously active speakers in a reverberant environment typically works rather well. Finally, for auditory attention decoding, we now use trials of length 30 seconds instead of 60 seconds used for the previous experiments. Let's first have a look at the decoding performance averaged over trials and participants. This figure shows the decoding performance when using either NVDR or LCMV beamformers to generate reference signals for decoding. On the one hand, when using the oracle speech signals, that is, without noise and interfering speaker, the decoding performance is about 89%, which is very good. On the other hand, when using the unprocessed microphone signals as reference signals, the decoding performance is only equal to about 77%. In general, it can be observed that the decoding performance when using beamformer output signals is larger than when using the unprocessed microphone signals. In addition, the decoding performance for the LCMV beamformer is larger than for the NVDR beamformer, which can be explained by the fact that the interfering speaker is suppressed more. Therefore, in the following, we will only discuss the results for the LCMV beamformer. Not unexpectedly, the best decoding performance can be achieved when using oracle reverberant RTFs, which is very close to the decoding performance using clean speech signals. When using estimated reverberant RTFs, a very poor decoding performance is obtained, which is due to the fact that the reverberant RTFs are not accurately estimated. When using anechoic RTFs, which can be easily estimated in practice based on DOA information, it can be observed that a very reasonable decoding performance of about 82% is achieved, and that there is hardly any difference between using estimated and oracle DOAs. Secondly, we consider the speech enhancement performance of the cognitive-driven binaural beamformer. More in particular, the improvement of the binaural signal-to-interference noise ratio, or SINR in short. This figure shows the SINR improvement for the binaural NVDR beamformer and the binaural LCMV beamformer for different values of the interference suppression factor delta, where the dashed red line indicates the SINR improvement of a frequently used fixed beamformer steered towards the frontal direction, which obviously does not perform very well for the considered acoustic scenario. First of all, it can be observed that a large SINR improvement can be obtained by the cognitive-driven beamformers compared to the forward-steered beamformer. Secondly, it can be observed that the binaural LCMV beamformer in general yields a better performance than the binaural NVDR beamformer. Therefore, in the following, we will only consider the results for the binaural LCMV beamformer for a specific value of delta equal to 0.1. When using oracle AED information, the best SINR improvement of more than 10 dB can be obtained when using oracle reverberant RTFs, whereas using oracle anechoic RTFs leads to an SINR improvement of about 5 dB. We're now moving one step closer to reality and using estimated AED, it can be observed that wrong AED decisions degrade the SINR improvement since the attended speaker will be wrongly suppressed. When using reverberant RTFs, the SINR improvement drops from 10⁻⁴ dB to about 6.7 dB. When using anechoic, RTFs, the SINR improvement drops from 4.9 dB to about 3.2 dB. This is then also the SINR improvement that can be really achieved by the system in practice when performing both acoustic scene analysis as well as auditory attention decoding from the binaural microphone signals. To summarize the findings from both studies, we first observed that the best decoding performance can be achieved when using the clean speech signals as reference signals, whereas the decoding performance significantly decreases when the reference signals contain an interfering speaker. Therefore, the decoding performance can be improved by generating better reference signals from the microphone signals, more in particular by suppressing the interfering speaker using LCMV beamformers. Secondly, I presented our cognitive-driven binaural beamforming system, where either a binaural NVDR or LCMV beamformer is steered based on auditory attention decoding. In general, for the considered acoustic scenario, a relatively large SINR improvement can be achieved, although AAD errors obviously degrade the SINR improvements. The results also showed that the binaural LCMV beamformer outperforms the binaural NVDR beamformer in terms of SINR improvements. An additional advantage of using the binaural LCMV beamformer is that it allows to control the suppression of the interfering speaker, which may be relevant in practice when the listener wants to switch attention between speakers. Now, in order to implement such a system in a real hearing device, there are still quite a number of challenges that need to be addressed. First, better acoustical signal processing algorithms could be considered, where we already tried out so-called convolutional LCMV beamforming, which combines dereverberation and interference suppression. In addition, where the considered acoustic scenario here was rather simple with two fixed speakers, more realistic and complex scenarios with multiple moving speakers should be considered. Secondly, for the EEG processing, definitely faster and more reliable decoding methods are required, where great advances have been made in the last couple of years, in my opinion. In addition, the system should also be tested in a closed loop, where the binaural output signals are presented to the user. And last but not least, less obtrusive EEG hardware is required, for example, using the C-grid system with electrodes around the ear. In all of these areas, it will be very exciting to work, in my opinion, in the coming time. Many thanks for your interest in my presentation, and I definitely hope to meet you in one of the virtual rooms in the coming days.